Welcome to ETAP Grid Code Solutions webinar. My name is Mohammad Zadeh and I'm your presenter today. In this webinar, I'm going to overview ETAP Grid Code Solution. We look at the modules and features, the engineering services and training we provided, and I'll go through the several demonstrations to show how the grid code information can be entered in the rulebook. How can we do the reactive power capability analysis, voltage and frequency, right through, far right through, and dynamic support. And finally, I will summarize this webinar. ETAP offers various modules and tools to perform grid code analysis. As we will go through this webinar, we will learn how to do PQ capability analysis in ETAP. We will learn how to enter voltage and frequency right through information and how we utilize those information in our dynamic analysis to verify and validate the performance of the inverter-based resources when it comes to the lower and higher voltage conditions in the systems. We do far right through analysis by placing a file in our dynamic analysis, and we'll see that how the system responds. You can do the same thing in the steady state and short circuit analysis as well. We can use ETAP modules related to the, again, the steady state, a smart inverter, dynamics, transient stability, combined with the UDM controller and power plant controller, digital twin, to do active and reactive power control. In this webinar, we're not going to focus on the active and reactive power control, and that's going to be done in upcoming webinar. Will we focus in more details on ETAP Power Plant Controller and how it can be used to verify and validate the active and reactive power control in the system. We also going to, in this webinar, cover dynamic voltage and frequency support. Again, ETAP, transient stability, in addition to the UDM or the primary controllers and PPC that we provide, can be used to do dynamic voltage and frequency support. For power quality, again, ETAP offers a certain tools to do harmonic analysis to meet certain grid codes. In this webinar, we're not going to cover that. There is a webinar that's going to cover that topic. Most of the grid codes mandate certain reactive power capability by power plants, whether it's renewable or conventional, when they interconnect to the system. In ETAP, the reactive power capability or PQ capability can be entered in the rulebook for assets, as we will see. It can be entered for grid code that needs to be met. And then in each asset, let's say in a DERs like wind or inverter, you can select that which, let's say, capability curve is applied. Typically, you pick a vendor. And then in the study case, when you do the analysis, you pick which basically rule you're gonna meet or you're gonna follow or comply with. What happens is that typically for this grid code, you need to have a voltage dependence for the equipment. So we provide a mechanism for the user to enter those data. We have a predefined rulebook as well that we are expanding to. So again, the demonstration, we go one more time in more details. Then we have the analyzer. So once you have the grid code information set up, you have the vendor equipment capability set up. Now we have an analyzer, grid code analyzer, that sweeps the P, the active power and voltage, and basically commands the DERs in the system, and then measures the power, the P and Q, at a point of interconnection as well as the voltage, and it generates a nice Excel report that includes all the information that you need for your grid compliance report. So it creates, let's say, PQ curves, VQ curves against the grid code. And if in this case that you see on the screen, if you're not meeting the requirements, you go, let's say, add a Statcom to system or capacitors and try to figure out what the size. So this grid code package here is not only just to make sure that you comply with a certain grid code. On top of that, you use it to actually size your assets like Statcom or capacitor in your system. Again, we will go through this in more details later on in this webinar. The other important piece of information when it comes to grid code is the voltage write-through. Another important requirement in the grid codes is voltage write-through. When it comes to the renewable or conventional sources connected to the grid, it is important for them not to immediately trip when there is a sudden voltage drop in the system. So typically the grid codes define a certain curve, a voltage write-through curve that the DER or a conventional generator needs to write through during the low voltage or high voltage condition. So in this case, you see a low voltage and high voltage write-through. So as far as the voltage is between these two curves, the DERs should not, or the DG should not actually trip, it should write through. So what happens in ETAP, user can actually enter the information related to the low voltage and high voltage write-through in our rulebook. And this can be assigned to the devices, the DERs in the model, as well as it's assigned to the grid code analyzer for verification. So then user can go apply fault or low voltage events and verify the trip condition. Again, we create a nice report for write-through for the user to figure out that if you are complying with the grid code or not. Very similar to the voltage write-through, we have frequency write-through. Again, grid codes mandates the DRs to write through the certain amount of over frequency and under frequency within a certain time limit. So those curves can be easily defined in our rulebook for the frequency write-through, and then it can be assigned again to the device, the DERs, as well as to the grid code analyzer for grid code analysis and compliance. Now, when it comes to the fault write-through, grid codes mandates typically to have certain amount of support if there's a fault in the system and the voltage drops. So typically the DERs are expected, if the voltage drops, to increase their reactive power contribution and reduce their active power if they tend to exceed their current limits. So in ETAP, the details of the current limit curve, the fault write-through characteristics, they're all available in ETAP. In ETAP 22, we are adding also negative sequence current injections to our WTG and inverter model. So that's also available. So several new grid codes like German codes or IEEE new standard for interconnections to the utilities mandate the capability to have negative sequence injections. So all these informations that are required are available in ETAP. Now, this can be used as part of the short circuit analysis when you do the steady state analysis, as well as it can be used in your transient stability analysis, dynamic analysis. When you put a fault or a low voltage event, you'll see that the actual DERs starts to increasing their reactive power contribution and reducing their active power. So you can verify that. If you have a black box model that we will discuss a little bit later in this webinar, then again, you have a mechanism in ETAP to add events in and see that how the DERs or the black box model reacts to that. One of the other things that we are also making it available is many models, standard models, they have a mechanism to define the current limits in terms of the points. Again, in the controller, we have options that user can, rather than using the curves that we have, predefined curves that we have in the editor for transient stability, they can actually use the user-defined points, the VDLs that are in the WEC models to define the current limiter behavior. Other things that we are also offering right now for certain grid codes, is also important to do the unbalanced current injection, negative sequence injections. We are offering a kind of a beta versions of our negative and zero sequence or all sequence components in transient stability. So that's also available in case you want to verify that how your system behaves, how your DERs behave during the unbalanced fault. There are many other features as well that in this webinar, we don't go to that details. In the upcoming webinars, there will be a chance to go through them. But Just to cover that, there are requirements in grid codes in terms of the active power control. Sometimes they're asked to have a capability to react to the different voltages or to react to the different frequencies. So we have a smart inverter in ETAP where the curves are available that how the inverter should behave for different voltages. And all these curves are in ETAP 21 could be entered in the editor. Now is also available in the Rulebook, and you can select it from the Rulebook. And it can be utilized again in the load flow analysis as well as in the dynamic analysis. The same to active power, we have the similar features with reactive power control. If you have a QV curve or volt var or watt power factor, whatever is there with different priorities, it can be entered in our inverters, and it can be at the rulebook level or at the editor level that can be used. Again, we go one more time through these, a little bit more details, some of these important features, and we look at how they work in ETAP. When it comes to the dynamic voltage supports, again, we have a QV droop in our power plant controller, as well as we have it in our primary controllers for the inverter. We also have a droop for, we have it for voltage, as well as we have a droop for frequency. So we have it again at the PPC level as well as at the inverter level. We look at it at the inverter level in this webinar. For the PPC level is going to be on September 21st webinar. The other aspect that are really important when it comes to grid code, especially once the design is done and we are just doing more of a verification, is to have a black box model. ETAP offers a dual DLL approach where vendor can have their own basically model written in any native language, or even it can be a managed language, but they can have their own DLL to do stuff. But we have another DLL, which that's why it's called dual DLL approach, that interfaces ETAP to the vendor, that gives lots of flexibility to vendor to they have their own interface for modeling, and it can easily create a wrapper in ETAP to interface their DLL to the ETAP environment. For vendors that are interested to create a black box model in ETAP, we have a development package, template, Visual Studio solutions in both C# and C++. We have a video tutorial, detailed document that we provide to vendors, and many vendors already started doing this modeling that make it available to the customer. When it comes to the engineering services, we offer, again, certain analysis like reactive power capability, right-through analysis, harmonic grid code study. We also help vendors to create a black box model. And if they have already a black box model in ETAP, we also, again, same studies, active reactive power control, voltage and frequency, right-through, far right-through. We support the users to perform this study if they are interested. However, we typically prefer the consulting companies who acquire ETAP to do those type of studies. But in case certain vendors are interested that we help them to do that, we are always welcome for that kind of services. We also offer in-person and online training. So if you're interested to learn how to do grid code studies in ETAP, you can always contact our sales team. They can help you that how to purchase in-person or online training related to grid code. So with that, let's start a quick demonstration in ETAP and look at the different features and modules that we have related to the grid code. Okay, for the purpose of this webinar, what I have here, I have a renewable power plant. It's actually a hybrid power plant. I have a bunch of PVs here. You see here, we can model the details of the PVs in this system. I have my battery. Again, some plants may have a battery, some plant may not have a battery. I have a Statcom. At this point, it's out for now. Then later on in the analysis, we're going to add and see how we can use the tools here to size our Statcom and meet the grid codes. Then I have my wind farm in this system. Again, it's a hybrid. I have about, I think, 20 or less than 20 PV. I have, again, about 18 or less wind and a 1 megawatt MVA battery. Now, The first thing that I would like to do is let's go to the rulebook first. So in rulebook, we have capability and control. So in capability and control, you see that we can enter or store our capability and control curves. Let's quickly look at some of them. The first one is the equipment capability, where user can enter the PQ capability, which is a voltage dependent PQ capability for a equipment. This could be a battery, this could be an inverter of a wind or solar. So as you see here is that user defines for each voltage level how the capability curve looks like. Again, this is mainly the data here is coming from the vendors of the inverter typically. Now, that's a place that we hold that information. Let's say that this is for a certain inverter. And then what happens is that let's say in your PV inverter, if I go to my PV array element in ETAP and go to the inverter, we added a section under the generation where you can say that my megawatt limits is actually based on a certain capability curve. Okay, and then you go and say that my capability is a certain rule or not. Okay, so let me just go to a capability revision that I have here. So if you look at the inverter one more time, you see that the capability is already assigned. Okay, and we have this for other elements as to you can go to wind turbine generation and you go to the WTG and you go to the capability and you see that the capability is already assigned. And in the rating page, you can say that, oh, I want to use a capability curves rather than a user defined curve or a control curve. So in ETAP 22, we added a feature that capability of the assets for PQ capability can be selected in the editor. What does that mean very quickly? This means that depending on how much basically active power you have, your reactive power will be limited. Let me just go to the curve that we have here for one of them. Let's do it here actually. Let's go to the rulebook, capability and control, and look at one of the equipment. What does that mean is that if the voltage is 100% and active power is 100%, for this inverter, no reactive power can be injected or produced or absorbed from the system. But if the active power is 92% or less, there can be 24% power that can be generated and 40% can be absorbed. So this is something that, let's say, a vendor provided for this inverter. Now, in analysis, we follow that. Means that if the active power is less, it opens for reactive power to be injected or absorbed from the system. If the active power is higher, again, the same thing. We look at the capability curve to determine. Now, one of the analysis that we do here is that now that we have all this capability assigned for these assets, a grid code typically mandates to basically measure the PQ capability at a point of interconnection or point of measurement. The grid code doesn't care typically about the individual inverters. It cares to the system as a whole at the point of interconnection or point of common coupling or point of measurements. Different grid codes, different standards, they use a different namings. Here I'm just following the IEEE naming convention that they use it point of measurements where the grid code needs to be met. Now, the way that we do in ETAP, we add a meter, we have also a grid code analyzer, and we add a grid code virtual grid. So one of the things is that in order to verify the grid code requirements, the voltage at the point of measurement needs to be held at a very specific value. So make this bus, the point of measurement, an infinite bus for the certain exact voltage, and try to see that how much reactive power can be injected for a certain active power. Now, we have a grid code analyzer that allows to do certain capability analysis. We can do a PQ capability or VQ capability. Basically, at different voltage levels for a certain power, we would like to know how much reactive power can be injected or absorbed from the system. So we can sweep the power, we can sweep the voltage, and we can determine certain graphs that how the system basically behaves, or how much reactive power can be absorbed or injected to the system at different voltages and different active power. So if I run this scenario, which is my capability no Statcom, let's run this scenario. So when we run this analysis, it creates a report we call Grid Code Analysis Report. As you see here, it gives you the list of all the devices in the plant, all the grid codes, capability rules used for these devices, the details of the grid code, not a grid code, this is more of an equipment capability for the devices that are in the system, the grid code capability, PQ capability and QV capability that's mandated by grid code. And I did not show that, but in the study case here, in the time domain load flow, we define a grid code at which rule we want to follow. Let's say in this case, you're following a certain grid code from the British standard or British grid code in this system. Then ETAP is going to do certain analysis. It's going to do, let's say, PQ capability at 97 voltage. Again, 97 is defined by the user, and user can change that. And it shows a graph here that shows the PQ capability. The red one is the calculated or the outcome of the analysis. The blue one is the outcome of the analysis, and the red one is the grid code. So basically, it shows that at certain active powers, let's say 10 megawatt, 15 megawatt, the plant can give only certain amount of reactive power, let's say in this case 7.44, but the grid code is asking for actually 9.9. It asks for more reactive power in this system, while we can only give 7.44. So you see that we are violating the grid code in this case. So that tool allows us to understand that, oh, we are violating the grid code. We have lack of reactive power on the injection side. On the absorption side, we are good to go. The same for the 100%. Okay, at the 100% voltage, again, you see that we are not meeting the grid code on the supplying of the reactive power. The same at the 103. And the other thing that grid codes sometimes have, they have the VQ curve. Again, if I go to one of the samples of these grid codes, so if I go to capability and control, and I go to the British standard for grid code, and then you can see the PQ profile that's mandated by grid code that's entered here, and then the QV curve that is also mandated by the grid code. So those informations are in the rule book, and is used by the ETAP tool to verify that if we are meeting the grid code or not. So as you see here, again, at certain voltages here between 95 to 105 that we have tested or swapped here, the grid code has not been met at lower voltages. There was not enough reactive power to be supplied to the system. Okay, so we are again violating the grid code in this scenario. Now, if we go and if you go in this system and say that now I'm going to add a Statcom. I've actually sized the Statcom by running few cases and realized that 8 megavar is a good size of Statcom for this system. So if I go and run a Statcom for this case, so this generates again the PQ capability report. And as you see here, now we have the Statcom in the system. Let me just show you the Statcom in the system. Statcom is in the system now. Now it creates an Excel report. In the Excel report, if we look at it, now at the 97%, you see that our capability extended, the reactive power supply extended. So you see that now we are meeting the grid code at 97%, at 100%, at 103%. And we can now look at the VQ curve. Again, you see that we are meeting the requirements here at the 15% active power generations and at 100% active power generations. So all these settings at what voltage and what power set points we want to do the PQ and VQ capabilities can be set in the grid code analyzer. And this generates this nice report for us. So this is what I have to cover for now for the capability analysis. Now let's move to the dynamic analysis. Grid codes actually mandates lots of dynamic analysis to verify the performance of the plant during the low voltage, high voltage, low frequency, high frequency, fault, balance, unbalanced conditions, as well as sending some commands to the plant to increase generations or increase the active or reactive power settings. Now, let's just start with again the rule book that for dynamic analysis, one of the most important things is the right-through curve. So if I go to the right-through curve, you see that the only application is only grid code. So user defines the right-through curve for a certain grid code. Let's say here is again a British grid code that shows a voltage right through, low voltage and high voltage right through, as well as you can define low and high frequency right through. So both of these rules can be defined here in this rule book that can be assigned, again, that can be assigned in the analyzer for right through analysis. So if I go to the right through analysis, here the grid code is available here that can be assigned. That this is the grid code that I'm going to verify at the point of interconnection. As well as for the equipment, we use the same grid code too. Here in this model, you can select the same grid code to be used for the right through. Keep in mind that if you are using a standard model like WEC model or generic models, you can use the same grid code both in the device as well as in the grid code at the point of interconnections. But if you're using a black box model, the black box model has internally all the set points related to the right-through capability. So you don't need to define it in the rulebook. It's rather be defined by settings by the vendor of the DERs and is provided as a black box model. So with that, now we have now the rulebook assigned for the right-through to both our DERs as well as the grid code analyzer. So what we are going to do, I am going to apply a three-phase fault. So again, we use a transient stability module. And in transient stability module, we can go to the events and apply a three-phase fault. I'm applying it at 0.2, and after 100, let's say 30 milliseconds, I'm clearing the fault. This is a three-phase fault at basically this bus right now. If I go one more time to my transient stability, let's go to the scenario. It's easier to find the stuff here. Okay. If I go to the event and three-phase fault, the fault is applied at the faulted bus. You see that when I'm doing a three-phase at this faulted bus, there's a fault impedance. So I have a control on how much fault impedance I want to consider to adjust the voltage. Okay. So you can use this mechanism to adjust the voltage, how much voltage you want to bring down at the point of interconnection. So let me run a three-phase fault here in this scenario and see what will happen. So before going and look at the report, so we applied a three-phase fault in this system. Let me just bring the sequence of operation here. You see that the fault applied at this bus, at this faulted bus, and the voltage at the POM is about 10%. Okay. And as the fault gets cleared, voltage comes up and the system dynamically behaves to correct the voltage. But you see that nothing trips, okay? One of the reasons that nothing trips is that if you go to the right through, I'm using this right through capability curve. And as you see here is that the minimum time for tripping for voltages above 10%, for voltages above 10% is 140 milliseconds. So if the voltage measured at my IBRs, which are somewhere here, okay, my IBRs are here. If I go to the fault condition, which was about after 0.2, a little bit if you go down, you see that voltage is about 20%. You see that at the fault was 0, at the point of interconnection went a little bit higher, but as the fault happens, the inverter-based resources, the DRs, start to inject more reactive power to the system and bring up the voltage. So typically it goes a little bit higher than what you expect. So in this scenario, it's go, let's say 20%, 20%, it should ride through for more than 140 milliseconds according to that curve. Now, again, you can look at you can go to ETAP and plot the bus voltage. Let's say you can plot the POM voltage here, and then look at the performance of the system. You can go at the time impedance that we have and plot the megavar and megavar in the system. If we plot the two side, probably it's going to be a better graph for us to take a look. So the expectation is that as the fault happens, the active power drops while the reactive power increases. And as the fault gets cleared, typically suddenly you have lots of reactive power because voltage recovers, and then the controllers drop the reactive power. Now, this Excel report actually summarizes what happens. First of all, it gives all the data that are useful in an Excel format that can be used in case you want to do some certain plots that are not available right now at ETAP. It gives you all the positive sequence voltage of all your DRs in the systems, all the actions, what trip, what didn't trip is available in this Excel sheet. All the ride-through curves that are used in the systems are available in this chart. And then we're going to have the V chart, the voltage of basically each phase at the point of interconnection or point of measurements. You have the positive sequence voltage, the PQ at the point of interconnection that I just showed it in the ETAP, the reactive current support, if you want to see that minus I1Q versus V1, which is a very important curve to show that how much reactive current increase during the low voltage condition is there. If in this case, I don't have a negative sequence, but if you have a negative sequence injections, you can see the negative sequence injection versus negative sequence voltage. You see all our positive sequence voltage of our inverter-based resources. You can see the power versus hertz. So you see at the point of interconnection, in this scenario, I just have a fault frequency. It doesn't change that much, but the active power drops. You can see the reactive power versus voltage. So you can plot that in case you have a QV support. You can take a use of this graph to show the relationship. If you have a frequency change, again, we'll see that there's a use to look at this graph and see how the system behaves. So one way to create a low voltage condition is through the fault and play with the fault impedance. However, there's an easier way to bring down the voltage in ETAP, and that's through the low voltage, basically, or voltage event in the transient stability. So what user can do always for grid code analysis, it can basically take a utility or a power grid that we have and do a voltage impact. Let's say I want to bring down the voltage at the point at the utility bus by 80%. And then reset that voltage back at a certain time. Keep in mind that that voltage impact used to be based on the operating voltage. Now we added a new feature that is based on the rated voltage. So you can always go 80% down and 80% back with a certain timing and see if the system performs as expected. So if I go here, let's say I run a low voltage right through for 0.2 in this scenario. Let me just run this case. And let's see what will happen. So I have this scenario that we run again. It creates a nice Excel report. If I look at my action, you see that nothing trips. Okay, again, you can go through the different curves and see how the system behaves. Now, if I go and a little bit increase, let's say fault doesn't clear in 240 seconds in this scenario. Let's say fault lasts longer. Let's add another, let's make this 6. And let's make the simulations about 8 and run this scenario. So I'm actually keeping the fault longer. Voltage drops to 20%, but typically it can go a little bit higher. If I go to my action, still you see that for this voltage, nothing trips. So in order to verify this, you can always go to the inverter, let's say, and look at the voltage here. Voltage is around 25%. A little bit probably goes higher. If we go, it's going to go to around 39% because again, inverters, they have dynamic support to inject reactive power. Okay, if we go just before the fault, you see that it's around 40%. Now, if I go to my rules, let's say go to my write through capability, okay, and look at the 40% voltage is around somewhere here, which means that it takes more than a second for this inverters to trip, okay? So if I go back to my study case, and let's do one thing, let's make this 2 seconds, and let's increase this timing to about 1.5, okay? So I'm keeping it for a longer time. Let's make it 1.8 actually. Let's make it 1.8. Okay, so I'm keeping it for 1.8, and let's run this case one more time. So in this case, I'm expecting actually the inverters in the system to trip. Okay, so again, you can look at it very quickly here in the action list. You see that all my inverters trip at about 100. You see that the event was at 0.2 and inverters start tripping. Keep in mind that what happens is that this curve here is a dynamic curve. So if I go to the right through, as the voltage drops, we are going through this case. We going down, and as we hit the time, let's say at 40% or 39% somewhere here, the inverters will start tripping. Okay, so again, you can evaluate the performance of the system that when the inverters trip and make sure that it meets the grid code requirements. Again, I've created scenarios for different voltages, for different low voltage cases, and check the system. Now, if you want to now verify a performance at high voltage conditions, you need now HVRT. Now, for creating a low voltage, we discussed there are 2 approaches. You can add fault, or you can add a voltage impact event. When it comes to the creating high voltage, either you need to have some loads that you're dropping, but typically it's very difficult if you want to create a scenario to create a high voltage in the system or add a capacitor maybe in the system. But in ETAP, to make that easier is to just go ahead and in the events at a high voltage right through impact, let's say that you can go and say that I want to bring the voltage of the utility 30% up and see what will happen. Okay. Again, in this grid code, if voltage goes above, let's say 20% or something, it's going to trip immediately. So again, if you run this scenario, high voltage right through, if the voltage goes 30% up, again, it creates a nice Excel report that you can go and see that all the inverters immediately, once they measure the voltage that goes, keep in mind, there are some filtering timings involved in the measurements of the voltage in the inverters. So if a little bit few milliseconds goes up, they're going to trip. Within 1 or half a cycle, 1 cycle or half a cycle, they're going to trip most of them. Again, you can look at the system performance in this scenario. I close the Excel. Let me open the report one more time. Again, the expectation that as the voltage goes up, the inverter starts absorbing reactive power. So if I go to the PQ charts, the expectation is that we are in this place here, just in this place, because we are tripping very quickly. The moment that the voltage goes up, then the moment we measure, we try to reduce the reactive power, we try to absorb more, but immediately we're going to trip because voltage is really high. Okay, so that's keep that in mind, that's happening here too. So for frequency right through, as I mentioned earlier, the right through basically rule defines how much frequency we can write through, the low frequency or high frequency. As you see in this graph, let's say if the frequency is between, for a 50-year system, is between let's say 51 and 49, it should write through forever. But if the frequency goes above, let's say 52, it should immediately I think it should trip in 10 milliseconds. So if it goes below 47 or it goes above 42, it should immediately, like 10 milliseconds, should trip. But if it goes, let's say, if it's between 51.5 and 52, it should take 900 milliseconds, something like that. So again, there are curves here that defines the behavior of DERs at the at the conditions that frequency deviates from the normal condition. Now, what we want to do here, we want to do two things. First, I don't want to run the simulations for, let's say, 10,000 seconds or 1,000 seconds. Transient stability, it takes some time. So what I'm going to do, I'm going to increase the frequency above, let's say, 52 hertz. So in ETAP, I have a case of high frequency right through. 1.05 means more than 5% in the 50 hertz system. If I run this scenario, the expectation is that the moment that frequency again gets measured in the controller of the primary controller, the moment frequency goes up, you see that the inverters are going to immediately detect and trip it. Okay, so the moment the frequency goes up, we're going to detect and we're going to trip, and that's what you see here. Now, the second things I want to show here, again, you can run this for other voltages and run it for a longer time to make sure that the frequency right through is met correctly, or you can do it for the low frequency right through as well. The other thing that I want to show here is that I want to do a frequency right through for only 2%. So when we are doing 2%, we are not supposed to trip for quite long time, okay? So if I run it for 2%, what I want to show is the dynamic support, okay? So I'm going to run this case. This is running for a little bit longer case for about a few seconds. And what I want to show that how the inverters behave during this higher frequency. So typically grid codes mandate inverters to reduce their active power to curtail if the frequency goes up. So if I go to action, you see that there is no trip in this scenario. Again, we are raising the frequency for 3 seconds and then we are dropping that after that. And if I go again to Rulebook, you see that for 2% that we are doing on 50 Hz, which is going to be about 1 hertz, we're not supposed to trip that we are not supposed to trip. So if I go to the we create a Phertz curve. In the Phertz curve, we plot the P, which is in megawatt at the point of interconnection, and the frequency of the system. So let me just go ahead here and change the type of this graph to combo, make it line, and then make it a secondary. And this gives a very useful graph for grid code compliance. It shows you that as the basically the red one is the frequency. As the frequency goes up from 60 to around 61.2, again, this is a 60-year system. The ETAP is smart enough that if the grid code kind of is related to 50 hertz, but you're somehow using it just for testing or for some demonstration here for 60 hertz, it scales that from 50 to 60 hertz for you. It scales it from 50 to 60, all the grid code. So in this scenario, you see that as the frequency goes up, okay, or in this scenario, as the frequency goes up, the active power is going down. The active power is going down. And then as the frequency comes back, the active power comes back to normal. As the frequency goes down, the active power comes back. Now, where this is coming from? This is coming from here. If we go to the primary controller of our inverter, you see that you can define in the RECA block for the active power control, there is a mechanism to enable droop function. So you can say that I can have a 5% droop for my active power control, and it can have a dead band. You can define a dead band, as well as you can have a positive reserve margin. So what does that mean is that in this scenario, I had a high frequency right through. Means that the frequency goes up, active power goes down. So that's very normal for the renewables to curtail in this scenario. But if frequency goes down, right now it's not going to do anything, because frequency goes down, renewables does not have anything extra to inject. They're always typically at their maximum. But in case a renewable vendor wants to reserve some amount of their capacity as a reserve for positive margin, then they can put a number here. So that, I want 5% of my generation capability to be always maintained for this low frequency support. Many not many, but certain utilities give incentives to the renewable vendors to actually do, again, dynamic support during the frequency drop. If something like this happens to the system, they pay for this kind of dynamic support contribution to the system. So if you want to simulate that in ETAP, you can always go ahead and do this positive reserve margin and verify and show and demonstrate that that's happening, okay? So again, we give all the tools required to perform this type of a study. You can do the same things for the reactive power droop. So if you want to do reactive power droop, you can do the same. You can enable it and you can put the value that you want for the droop and show that if the voltage drops or voltage increases, all the assets, they're going to contribute. Keep in mind that the right through, that you saw that we were doing the right through, far right through on these inverters, that if the voltage drops, the inverters, they're going to react, they're going to inject more reactive power. This is called far right through, which is typically for voltage below, voltage drop more than 10%. If voltage goes below 90 or voltage goes above 110. But even within that 10% dead band that we have, if you want to have some sort of a droop, within that 10%, you can use the controller to set that 10%. So keep in mind that this droop for reactive power is during the normal conditions. Within the basically plus minus 10% you're dealing. You see that the dead band here is only 1%. So between 1% and 10%, you use the droop for QV. Beyond the 10%, it's going to be far right through, okay, or low voltage right through or high voltage right through. Again, due to the timing, I'm not going to demonstrate this here at this point. So with that, I'm done with my demonstrations. Let me get back to PowerPoint that I have and summarize this webinar. So what we did in this webinar, we first overviewed ETAP Grid Code solution. We talk about the various modules and features we have. And I would like just to emphasize that in this webinar, we demonstrated what we have in the rulebook. We showed reactive power capability, voltage and frequency right through, far right through. We look at the frequency dynamic support. We have also the voltage dynamic support if you're interested. The other thing that also we emphasize is that ETAP also offers tools for harmonic analysis within grid codes. There's another webinar related to the power plant controller, where if you want to see more on the active reactive power control through the power plant controller, you can watch that webinar. So with that, I'm done. Let me know if you have any questions. You can contact ourselves if you have any questions related to that. Thank you.